So we're going to start with number 11. This is an aldol condensation. And so the first piece of information we need is which of these alpha protons are we going to remove. So you've got a choice between the one rendered in green and the one rendered in white. The one rendered in green is more accessible. This is a non-nucleophilic base, so it is going to generate the kinetic enolate, which is the one with the lowest energy of activation. And because it is to the exterior of the molecule, so to speak, it'll be the one that's removed preferentially. So even though we don't need to show the mechanism for this reaction, I think this is an excellent time to review the mechanism of the aldol reaction and all enolate reactions, really. So diisopropylamine is our conjugate acid. And I'm going to show both of the resonance structures for this enolate. Normally we would think that the more stable charge would be when the negative charge is on the carbonyl oxygen, because oxygen is more electronegative than carbon. However, the carbon-oxygen bond is such a low energy bond, and by that I mean it releases a lot of energy when it's formed and requires a lot of energy to be broken. The carbanion is going to be the major nucleophilic species. So this species that is rendered in orange is going to be the species that we use to rationalize the aldol condensation. Now, if we look at the enolate, and when I do this, I always start with the enolate. And I'm going to show it attacking a molecule of benzaldehyde, which is a very typical aldol electrophile. So most reactive nucleophile attacks the most reactive electrophile. When we go to draw this, I like to just draw the nucleophile first. Then in a dotted line, I'm going to indicate the bond that I am making. Notice that we're going to make an alpha-beta bond. So the alpha carbon is the carbon on which I had the carbanion, and the beta carbon is going to be what used to be the carbonyl carbon in benzaldehyde. So here's the carbon from benzaldehyde, and of course we are going to have a benzene ring. Once we draw this, we can fill this in. Now we will have an O-, which will eventually become an OH, but the driving force of conjugation is so strong that this will spontaneously eliminate via the beta elimination and yield the very highly conjugated alpha-beta unsaturated carbonyl. And so you have a really nice array of sp2 hybridized orbitals. And so I'm going to circle this array. This is a 10 pi electron system, and this is going to be our major product. So as we go to look at our answer choices, A is the structure that's most consistent with our mechanism. So for number 11, the credited response is A. Let's take a look at number 12. We have really what is a Heck reaction, so I'm going to take the time to draw the structure of the two major reactants. And really what happens in a Heck reaction is that you are going to couple this alkene to where this halogen is, and this alkene will always attach in the trans position. So when we attach this in the trans position, the best answer is going to be A. B is in the cis position. B is in the cis position. C is a meta-disub. So the substitution will occur where the halogen was. And of course, D does not have the alkenyl group. So A is by far and away the best answer. I guess I really don't need to draw that after all, but this is a hallmark of the Heck reaction. It's a palladium coupling reaction under alkaline conditions, and I will attach the alkene directly to an aryl group. You can also use this to couple alkenes to alkenes, and so it is a reaction that I feel like you definitely need to know for your final exam. We also have the Suzuki coupling. You're simply going to take the molecule that has the bromine, the molecule that has the borate, and you're going to couple them directly together. And so the best answer choice is also going to be A. Make sure that you are familiar with the Heck reaction, which is illustrated in number 12, the Suzuki reaction, which is illustrated in number 13, the Grignard reagent, and also the Gilman reagent. Those are all very important organometallic reactions. In identifying the most alkaline compound, you need to realize that alkylamines are always going to be more alkaline than arylamines. Alkylamines will weakly donate electron density, which makes the lone pair on nitrogen more reactive. So the best answer is going to be A. The worst base or the weakest base will be C, because that lone pair is needed for aromaticity. And in D, it would be the second weakest base because the lone pair is in resonance with the ring. B would be the second strongest, that's pyrazine. The lone pair is localized on the nitrogens because they're participating in a double bond, which means that the lone pair is going to be orthogonal to the plane where all of the unhybridized p orbitals lie. If we look at number 15, and I want to go and actually put this out for you. So what we wish to do is to start with benzene. And we're going to produce an acyl hydrazide that is para to a bromine atom. This is a very unusual functional group. This is used to synthesize 1,3,4-oxidiazoles, which is one of my research interests. So let's talk about what we need to do. You must add the alkyl group first, because once you add the bromine, Friedel-Crafts reactions are shut down. So this cannot go on first. You also can't add an acyl group first. You must alkylate first. So we can do this by about any method we wish. Let's go ahead and just do a simple methylation. So CH3Cl with AlCl3. And then we can brominate, and the bromination will occur at ortho and para. So we'll have to separate the isomers. We can then oxidize the methyl group with KMNO4 or any kind of oxidizing agent. Once we have the acid, we can convert that to the acid chloride with SOCl2 and pyridine. We can convert that to an ester with methanol. And then we can convert the ester to the acyl hydrazide with hydrazine. 5-step reaction. So if we go back and look at the reagents, of course this affords the target molecule, which is this guy right here. So if we go back, we see we have an alkylation, a bromination, an oxidation, and a esterification react with hydrazine. That actually works quite well. Acylation would not give us a para-substituted product. Bromination would not give us an alkyl group. If I do alkylation and oxidation, it becomes a meta-director. So indeed, C is going to be the answer that is going to be correct. So for number 15, the best answer is C. As in, C, I got another one right. Okay, so for this guy, C is the credited response. Let's move on to a little biochemistry now. For number 16, when pyruvate, a key glycolytic intermediate, undergoes reductive amination in the Cori cycle, which alpha amino acid is produced? You need to know a little bit about amino acid structure to answer this question, or you can simply memorize them, I guess. So pyruvate has the following structure in the Fischer projection. And when this undergoes reductive amination, so essentially you're going to have as a reactant ammonia, and as a product you're going to have water. We produce an alpha amino acid, an L-alpha amino acid, in which the R group is methyl. This is better known as alanine. 1-letter code abbreviation is A. 3-letter code abbreviation is ALA. So going back to the answer choices, alanine, answer choice C, is the credited response. Again, you need to know a little bit about alpha amino acid structure to answer number 17. Lysine has an epsilon amino group. So let's take a look at that for a moment. So I'm going to draw the chain of lysine just a little bit differently. Here's the backbone. Of course, this is the alpha carbon, beta, gamma, delta, epsilon. It's an epsilon amino group. You got 2 positive charges, 1 negative charge. The overall charge at physiological pH is going to be +1. And this is lysine, which gained some notoriety in Jurassic Park because it was the amino acid that was deprived to the dinosaurs. 3-letter code abbreviation is LYS. 1-letter code abbreviation is K. So for number 17, the credited response is B. Number 18, why are all naturally occurring lipids comprised of an even number of carbon atoms? They're all derived from acetyl-CoA. And so acetyl-CoA will undergo a self-Claisen condensation. Let me take a moment to show that to you. Of course, the thioester is really complicated. We're going to abbreviate it. We can make an enolate, and we can have it attack the carbonyl of another acetyl-CoA molecule. you're going to get additional elimination, which is the process of substitution. And I'm going to go this is the bond that we make. Of course, we're going to reform the carbonyl, and this other sulfide will act as the leaving group. So now we have 1, 2, 3, 4 carbons. So we'll always get an even number of carbons because all of the carbons in lipids and fatty acids are going to come from acetyl-CoA. So as we consider our answer choices, best answer is going to be B. Number 19, we want to identify the Fisher projection that represents D-galactose. A couple of things to remember here. One would be the original structure of glucose in the Fisher projection. So we went over this numerous times in class. So we're going to have hydrogens oriented this way. And I'll put the OHs in red. This is the Fisher projection for D-glucose. Galactose is a C4 epimer, which means carbon 1, 2, 3, 4, 5, 6. Carbon 4 has its configuration flipped, but everything else stays the same. So remember, an epimer is a specialized type of diastereomer. Mannose is a C2 epimer of glucose, but galactose is the C4 epimer of glucose. And so carbons 1 and 6 are the same. Carbon 2 is the same. Carbon 3 is the same. Carbon 4, however, is inverted. Carbon 5 is the same. It's important to see if I were to reduce the aldehyde to an alcohol, so the alditol of galactose is meso. It will not rotate light. The aldonic acid is also meso. So the aldonic acid of galactose is meso. Now the alderic acid makes an acid only from the aldehyde. That will not be meso. That will be optically active. So as we go back and consider our answer choices, we want some symmetry, and it looks like the best answer choice is going to be C, and C should have an oxygen hydrogen in place of this hydrogen. So 19 should be C. Let's do one more before I stop this particular screencast. We're looking at the benzyne intermediate, and remember from the benzyne intermediate, it will look like this guy right here, and the NH2 can attack this carbon or this carbon. So again, we see a typo in this one. C is the proper answer, but there should not be an amino group off of the triazole ring. This is 1,3,4-triazole. The triazole should not have an amino group. So the intended answer for number 20 was C. So I'm going to stop this screencast now. I'll be posting some more over the weekend, and we'll have all 50 of these up before I'm finished. I'll also be posting some mechanisms from Orgo 1 that you will want to know for your final exam.